Hi, I'm Peter Rowlett.
And I'm Katie Steckles. And Peter, what's today's mathematical object?
Well, it's extremely mathematical. I brought a thermometer.
Right.
And it's stuck in a cup of tea. In fact, could you just tell me the temperature on the thermometer?
That looks to be 67?
67. It's not a very good thermometer. It's a thermometer for putting in tea, which is apparently a thing, and it measures the temperature every 2 degrees. So it's not the most accurate thing in the world. There's a line every 2 degrees, and you're right, it's sort of between two lines, so we're going to say that's 67. The reason I've got this is I thought we could talk about differential equations and rates of change and fun things like this.
Right.
And I have a class where I do this as a stunt, and we'll try and do it now, where we use data from the thermometer to make a prediction about the future. And the reason for that is that there's a really nice little story you can tell about differential equations where you start with some physical principle that you want to investigate, and then you do some calculus on it, and it makes an equation. And a nice example to lead with this is if you start with constant acceleration, well, acceleration is the rate of change of velocity. So if you integrate your constant, you've now got velocity. And then velocity of the rate is the rate of change of your distance. So if you integrate it again, you get a formula for distance. So now you've got equations for distance, velocity, and acceleration, all just starting from this basic principle of constant acceleration. And that's very nice. And you can use that. I have an example where there's been an accident and there's a skid mark on the road, and you can use that to work out whether the car was breaking the speed limit or something like that. And it's all very hypothetical and fictitious as an example, but it's perfectly nice. Then I have, there are things like population growth is one. So you can say the rate at which the population increases is in proportion to its current value. And that gives you a differential equation because you've got the rate of change of population is proportional to current population. So it's equal to current population times a constant.
Yeah.
And again, you can solve that as an ODE and get yourself an exponential growth equation. The other way around from that is radioactive decay, where the rate at which a lump of material decays is proportional. It decreases proportional to its current value, so you end up with the same thing with a minus sign in. So you end up with radioactive decay rather than exponential growth. You have exponential decay, and so on and so forth. And you get these sort of nice sort of little examples, which are it's not the most realistic model of population growth because it doesn't take into account any sort of limiting factors or anything like that. It does fairly well on radioactive decay, I think, but generally you end up with this quite simple model, and then you can work some stuff out and go, oh look, I worked some stuff out, and that's that. And what I quite like about this example is that you make a prediction about the future. So Newton's law of cooling says that an isolated body in a room, where the isolated body has a different temperature than the room as a whole, so like I've got a cup of tea in this room, the cup of tea is hotter than the room, that isolated body will lose heat to the surroundings. And it isn't that it will lose heat forever until it freezes. You know, if I leave my cup of tea here, it's not going to freeze. What's going to happen to it long term is it's going to tend towards the room temperature.
Yeah, you kind of equalise.
So what it is the rate of change of temperature is proportional to the difference between the current temperature and the room temperature.
Right.
And that's an ODE, and you can solve it in the usual way, and then you get this slightly more complicated but not horrendous equation for Newton's law of cooling. And then this equation involves the initial temperature, the room temperature, and a rate constant, which tells you how quickly the temperature is decreasing. While we're at it, do you want to take the temperature again?
Okay, yeah, that looks like 62.
62. So write that down if you're playing it along at home. 62.
Yeah, we're putting it in a spreadsheet.
Yeah, I am putting it in a spreadsheet. It's a bit of a cheat, that. I
mean, it's the most useful way to store any information, so that would be my first instinct.
Yes. Okay, that's good. So what I'm doing then is The room temperature, you can sort of just assume, I'm going to assume it's 20. Actually, the room temperature doesn't have a huge impact on what's going on. When you actually get the final equation, changing the room temperature by quite a bit doesn't actually change the prediction a huge amount. So that's good, I guess. You need the initial temperature, which was the first measurement we took. So we took a temperature of 67, and then 5 minutes later we took another temperature that was 62, and then using those two pieces of information, you can calculate the rate constant, the rate at which it's decreasing. And then we can make a prediction. So, for example, you sort of arbitrarily choose where you want the temperature to end up. But so if in class I say 50 degrees, because in class I derive the ODE properly, and that takes a bit of time. But 50 degrees is a little bit cool for a cup of tea, for my liking. Anyway, I've put, if I put 57 degrees in here, then it thinks it's going to reach 57 degrees at about, in about 4 minutes from now. I was going to say the time, but that's not meaningful if you've listened. So in 4 minutes from now, we think it'll be 57 degrees. So we can have a look at it then and see whether our prediction becomes true. But what's quite nice about this is that you rather than it being a toy example, you derive an ODE, you calibrate it using some data that you gather live, and then you make a prediction. And there's this sense of, like, we don't know whether this is going to be right or not. And sometimes it is, and sometimes it's not. And there are a bunch of reasons for that, which I think are quite interesting. So you're making assumptions. You're making assumption about the room temperature, and you're also, there's a whole load of sort of measurement errors and things like this. You're also, in Newton's law of cooling, all models are approximations of reality. And one of the ways in which Newton's law of cooling is an approximation for reality is that the room temperature doesn't change, when really what you've got is a hot body emitting heat into the room. So it does
so
change.
There'd be a tiny,
but
like they're not, it's not just dropping, they're getting closer to each other sort of
yes,
thing, but
absolutely.
one is moving more quickly.
Yeah, in the same way as when you jump, you're moving towards the Earth and the Earth is moving towards you.
Yes.
You don't really notice
Yeah.
that the Earth is moving towards you, right? And then there's a whole load of problems, like I'm using this thermometer that it's really hard to get accurate measurements from because the first time I did this, I was in a science department and I went along to the storage and they had thermometers, and they were the kind of thermometers that you use in chemistry, and I thought, I'm not quite sure what they've been used for, and anyway.
Oh, yeah, you don't really put that in your tea, do you?
Yeah.
So, yeah.
And part of the gimmick is that I then drink the tea once it's drinkable, right? So I bought, apparently you can buy thermometers for tea, specifically designed for tea, and this is what I've got. And for the purposes of worrying about when you know, as you're making tea, apparently you don't need an incredibly accurate thermometer. The other thing is that the time that I'm using is reading the time off my phone, and that's to the nearest minute. And
right.
If I wanted to do it properly, I should really be doing it to the nearest second. But yeah, well, who worries? So there are a few reasons for that it might be slightly off, I suppose, when it actually comes to it. Apart from that, it's just to say really that I think this is sort of the real power of differential equations, is that from a really simple starting point, you make a differential equation, you solve it, you calibrate it with some data, and you can test that assumption. And it really, I think, shows to students that they've got this experience of, it's the future, he can't have rigged it, it's a cup of tea, so this is actually working. This isn't like the skid mark on the road where Peter says the car was breaking the speed limit, but you know, so what? It was just an example. It's the actual sort of thing where you can do it properly. So, do you want to take the temperature again?
I think it is now 4 minutes after we last took the temperature.
Yep.
It looks like it's just slightly above 56, maybe quite near 57.
Okay. So, if I put 56 or 57, the thing about this is that the prediction was that it would be 57 at some point in the 10:18 minute.
Right.
But we aren't really using a clock to the nearest second. So I'd say that's fairly good as an accurate prediction.
Pretty impressed with that, yeah.
Good. So that, for me, I think, is nicely the power of mathematical modelling, that we take a basic principle, we derive an ODE, we run that ODE, we calibrate it with some data, and we make a prediction about the future. And I think that's lovely.
That's really nice, yeah. I think, like, this reminds me of, there's like a classic puzzle where you say, if you are making a cup of tea for someone, do you put the milk in when you make the tea? If they're not going to arrive until later, do you put the milk in straight away, or do you put the milk in when they get there? If you want the tea to be maximally hot when they arrive.
Right.
And because of the way this equation gives you a formula for this, you can actually see, because it's proportional to the difference in temperature, if you put the milk in straight away, it drops the temperature.
Yeah.
So the cooling happens more slowly.
Yeah.
But if you put the milk in when they arrive, the cooling happens more quickly because there's a bigger difference. And then when you put the milk in, the temperature drop is still roughly the same.
Yes.
So it will actually end up being warmer if you put the milk in straight away and let
Yeah.
a slightly cooler cup of tea cool more slowly for the same length of time.
Yeah, that's nice.
So it's a nice little kind of puzzle to make you think about logically what would happen, but you need to understand the principle that the cooling is proportional to the difference in temperature. So.
Yes. Yeah, that's good. And that's not always intuitive, although once you've talked about it, it does. And I always say this thing about, if I left this in the room, it wouldn't just spontaneousally freeze. There is a sort of limiting exponential.
Yeah, I mean, this is entirely
decay.
physics, so it's outside of what I'm really interested in. But no, tea is very much in my wheelhouse.
Yeah.
But yeah, I think it's really nice that this is an example of a physical system that can be modelled in such a simple way. And as you say, there's lots of minor assumptions and actual, variations in temperature and things. But yeah, you get this constant that encodes the rate of cooling. And I guess that depends on the size of the cup and
and what the cup's made of and other sorts of
what flavour of tea it is. And
presumably,
kind of thing,
that must be encoded in the constant. Everything in this model is encoded in that rate constant, and you don't have to worry about it.
Yeah, that's lovely. I mean, I remember a few years ago there was an event at a science festival that I was involved with that was the science of tea, and they had this really nice. It was a mix between a tea expert who talked about these are the right temperatures that you need for brewing different types of tea, and I imagine they're the kind of person that owns a tea thermometer.
Absolutely.
But then there were also a couple of scientists, a materials scientist and a chemist there, talking about all the properties of tea. There's some really fascinating stuff in there about how a kettle boils and how how that changes the temperature of the water and that kind of thing. But yeah, this is lovely.
Nice.
So I'm on Twitter as @Steckles.
And I'm at Peter Rowlett.
And we both blog at aperiodical.com, which is also where you can find more episodes of this podcast.
And if you have any thoughts or suggestions or want to talk about tea, you can email us objects@aperiodical.com. The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.